Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm Savas Parastatidis, and I work for external research, as Darren said. And today is my last day with external research. I'm moving to live search. It's a product that you might have, a service that you probably haven't heard. But it's we're trying to do search as well. So, or as a friend of mine who's using Google a lot thought that the service is about searching for extraterrestrial life because of its name. So I've known Paul Watson. I'm introducing here Paul Watson, and I've known him for 12 years. And the reason I'm doing the introduction is because I was his PhD student and then worked with him as a postdoc and as a researcher later in my career. Well, Paul, if I've done anything good as a researcher, I owe it to Paul. He's taught me everything that I know. And so you can blame him for everything that I've done wrong. So I met him in 1995 when I interviewed for the PhD position, and then I started working for him in 96. And as I said, I've learned everything from him. And it was apparent that I was going to learn so many things, even from our first meeting, my first PhD student, the supervisor meeting. I will never forget. I'm very bad with names, so usually I find myself in situations where I don't remember the names of the people that I'm talking with. But I will never forget that first meeting and the fact that Paul introduced me to the concept of cricket, and that there was one Greek player that played at the test cricket match, and that was Xenophon Velasquez. So it's just that his name is just with me. So here, the first piece of knowledge that I've heard, that I've learned from Paul. After my PhD, I went to do my military service, and I just decided to do a break. In Greece, it's compulsory, and I needed to jumpstart my career. And surely enough, Paul was there for me. He offered me a job at the University of Newcastle as an architect. And how do I repay him? I'm characterized by the community as a troublemaker. And for some of you may know that I published a paper, and to demonstrate Paul's ethos. At the time, there was a lot of turmoil in the Greek community because of that paper, and Paul's boss wanted to find out more about what was going on. And so he asked for a teleconference. So I go to Paul's office before the teleconference, and I say, look, I'm a young researcher. I can probably restart my career again. I'm going to take full blame for this. I will say, didn't know anything. It was all my fault. Paul said, no. I'm going to fully support you. You have nothing to worry about. Demonstrating, how he cared about the people who worked for him. And then the phone rings, and here is Paul's boss, saying, guys, you don't have to worry about a thing. I just want to know what you're saying about and what the problem is and what the issues are. I just want to understand. And sure enough, that was Tony Hay, for whom I ended up working for a couple of years. And that's Paul. He started from the University of Manchester. He worked for ICL. He built big database machines like the Golders machine. And then he moved to Newcastle, where he's a full-time professor. He's been doing just amazing stuff. The eScience group that he's been leading there has touched in so many disciplines and has done so much interesting work in bioinformatics, neuroinformatics, if I remember well, transport engineering, social informatics, chemical engineering, and I think we're going to hear more about that, computer science. And he has numerous PhD students, researchers. He's been a great innovator, working with the industry, his supervisor, and a friend. So despite my feelings about cricket, that I'm sorry that to the UK people, I just don't like it. One of my best days before I left from Newcastle to come and work for Microsoft was spending a whole day at a test cricket match with Paul, and I will never forget that day. I'm very much looking forward to what Paul is going to say. He's showing us the way in cloud computing, and I'm just want to invite him here to talk about it.
Okay, well, thanks, Savas, for that. Should be on now. Yeah, so it's been fun working with Savas over the last 12 years, and I'd like to wish him every luck in his new job. I want to talk today about some work that we've been doing with neuroscientists for a few years. I became interested in working with neuroscientists because, although I'm a computer scientist who's worked on artificial computer systems for about 20 years, I always felt that trying to understand how the brain worked was really the greatest remaining challenge. And I was interested in talking to people who did that all day, every day, and wondering how we could work with them. And the attraction of working in this area isn't that it's obviously of interest to biologists how the brain works, but also the implications of understanding more about the brain cut across many areas. So medicine, of course, many drugs operate on the brain, and also in my own field, computer science, then the brain is much better than artificial computer systems, software and hardware are at so many useful tasks. For example, I can look out and recognize some old friends here and think about what we've done together in the past, and imagine trying to construct some software and hardware which could do that. It really just isn't possible at the moment. So the hope is that by understanding how the brain works, we can also understand how to build artificial software systems which help us with these tasks. And I'm not alone in being interested in this. I was quite surprised to discover that there's actually 100,000 neuroscientists around the world, and they work in many different areas. So some of them are down at the genomic molecular level. There are those who work on neurophysiological data, so time series, understanding the patterns of spiking behavior in the brain. Then we can go up a bit to anatomy, so understanding the wiring of the brain. And then there's at the top level, understanding the behavior of subjects and how that's reflected in brain activity. And all of these scientists around the world are collecting data. And this is where the problems start, because as you can imagine, it's quite expensive to collect data from brains. And what we'd like to do is to get as much value from that data as possible. But there are a number of problems with doing that at the moment. And the effect is that we're really not getting as much value as we should do from the data that's collected. So one problem is there's really no vehicle by which people can easily share the large amounts of data that they collect. So a typical way to share at the moment is to put the data onto a DVD and put it through the post to somebody who you've met or you want to collaborate with, who you think might be interested in the data. But even if you do that, then there are problems. So it's quite typical that when you collect data in a neuroinformatics experiment, what you do is you use a rig which is provided by a manufacturer, and it's typical that every manufacturer has their own proprietary file formats that they use to store the data. So even if you could give your data to another scientist, the chances are that their analysis routines wouldn't work with your data. And then you have the problem that even if their analysis routines do work, how do they understand what the data means? What was the nature of the experiment? What drugs, say, were used on the slice of brain tissue from which the data was being collected? So there's no common standard for metadata. It tends to be locally described in lab books or sometimes in a fairly free textual form in computer systems. So again, even if you could copy the data across to a colleague who could read the data with their analysis routines, then there would be a problem with them understanding the circumstances in which that data was collected, and therefore how to interpret the data. So the effect on the community of neuroscientists is that really there's a shortage of general analysis routines which can be used across the data sets that are being collected around the world. And there's a shortage of collaboration between those people who are good at collecting data and experiments and those people who are good at doing the analysis of that data. Everything tends to be slightly balkanized, so people collect data and do their own analysis on it, rather than being able to take advantage of the expertise of others who are working in different organizations, different labs, and may have complementary skills. So this problem of data being, effectively data not being either lost or it's not getting value from it, it's not just in neuroscience that we get that. As Savas has said, at Newcastle we worked across a number of different areas of eScience, and it's quite typical to see this in many areas. And so I was pleased to find a paper by a guy called Jeff Bowker who looks at the way science operates, where he talks about this standard scientific model, and he says that things happen in 3 stages in science. So first of all, people collect the data, and then they analyze it and publish papers on it, and then gradually they lose the original data. And I think that all of us who are used to working with scientists have seen that in many different forms. And so you have these problems which go at the heart of eScience and science, that we're not getting value for all the data that we collect. We can look at papers and we see conclusions, we might see summary graphs, but we often can't go back to the original data and say, well, that just seems a little odd, it's not what we'd expect, let's reanalyze the data. We can't do that. And so you get this inability to replicate experiments, something which is considered to be very important in science, but is often impossible with the way in which we make information available at the moment. And I would also claim we have another problem nowadays in science, which is, of course, lots of the data that we use is generated not directly from experiments, but it's secondary data produced by analyses. And again, you could make this case that there are 3 stages for these programs, for these codes. That first of all, we write codes and apply it to those codes to data. And then we publish papers which use those codes, and then we gradually lose the original codes. So I think there's an analogy there between data and the codes which they analyze. And you can draw exactly the same problems as well as the result of not being able to preserve and share the codes that we use to analyze and create data these days. So what I'll talk about today is I will talk a bit more about neuroinformatics. It's been a particularly challenging area of eScience. I'll talk about some of the specific things that we're trying to do with the scientists. I'll talk about the project CARMEN, which is trying to address some of these issues. And one of the things we've been doing in CARMEN is try to explore the use of cloud computing for eScience. So what I'll do is I'll talk about what we've done. And as it's probably early days for cloud computing for eScience, I'll try to give some of the early lessons that we've learned by trying to use this emerging technology to do the work that we want to do with the neuroscientists. And then I'll talk about things that are just coming along, these commercial clouds like Amazon and Microsoft Azure, and how I think those will affect the way in which we do eScience. So if we look at the particular sort of neuroinformatics that we're interested in the CARMEN project, then it's about electrophysiological data. So it's about understanding the spiking behavior of the neurons in the brain. And typically what happens is that an electrode is inserted into a piece of brain tissue, and then you get a signal out of there. And you can see the signal at the top there with some spikes in it. Now, because there are a lot of neurons and 100 billion in the brain, and they're very small, and electrodes are relatively large, you can't just navigate an electrode into a single neuron and then just get the signal from one neuron. So what you do is you put an electrode into an area of the brain, and you get the signal which is from all of the neurons which are around that particular electrode. So the first stage of analysis is to try to work out the set of neurons from which that composite signal was produced, and then to split it up again. And this is called spike sorting. You can see the effect of that in the middle in the middle here, where some analysis has determined that there's actually 3 neurons that are being picked up by this particular electrode, and those are the spikes from those neurons. And then what you do is you have to do some analysis. So typically there's some basic statistical analysis, things like rate analysis, because many people feel that the rate of spiking is an indication of activity going on in the brain. So this then happens to those separated out signals. And then people try to draw some analyses from that. So when I first got interested in this area, I went to our local university bookstore and went into the medical section and bought a book, Basic Introduction to Neuroinformatics, it was called. And it's about this thick. And settled down at home one night in my favourite chair with a cup of tea and started to flick through the pages, started to read from page 1 in detail. And after about 100 pages and 2 hours later, then I was swimming with all of these different names for different parts of the brain and information about what they call the different parts of neurons and synapses and so on. But I still hadn't got to the section which described how the brain actually works. So I started to flick through more quickly and look at the contents and the index, looking for this particular section, and didn't find it. And so I went in and to work and talked to some neuroscientists the next day, and they said, well, no, nobody's really sure how the brain works at the moment, so you won't find that particular chapter. But what they said was they would like to write that chapter, so that's their goal through their career, is to actually understand how brains work and to be able to add that to the literature. So really a lot of once you've done this basic analysis, a lot of the effort that's going on is to try and understand how this neural code actually works down here. I'll give one specific example of the sort of work that scientists in the project are doing. So this is some work that's being done at a local hospital in Newcastle. So every month a patient presents themselves at the hospital who is suffering from very severe epilepsy, and drug treatments are tried, but for about 12 patients a year, there's no alternative other than surgery. So drugs can't control epileptic seizures, and the only way to retrieve the situation is try to remove the part of the brain which is felt to be causing these problems. And so what the surgeon would like to do is to get information in near real time as he does the operation, which can guide him as to where to remove tissue from the brain. So what I'm going to do, see if that works. Going backwards. Okay, so this is what I wanted to put up. So this is a warning. So I'm going to have a couple of slides which do actually show an exposed brain, just to give you a feel for how things work at the moment. So do look away now if you don't want to see this, and I'll tell you when it's over. So this is before the operation, where the surgeon has exposed the part of the brain in which he feels the problem is occurring, and he wants to work out exactly which part of that exposed part of the brain to remove to solve the problem. And so what he does is, I talked about use of electrodes. So he places these electrodes. You can see 2 sets of 4 electrodes there, and he actually moves those around, looking for characteristic patterns which indicate that there's a problem with this part of the brain. And at the moment, what happens is he gets a very direct representation of the spiking behavior. So he just gets this composite signal, and he moves them around until he sees the sort of pattern that he thinks is okay, and then he removes that particular area of the brain. And you please know I don't actually have a slide on that. So if I so I think that if you look at those sets of 4 electrodes, that's probably about 4 or 5 centimeters for those electrodes. Yeah. So what we're trying to do in CARMEN then is to support people who are trying to do neuroscience, including that surgeon. What the surgeon would like to do is they would like to, as the data comes out of the brain, they would like to be able to analyze it and get some statistical analysis which would help them to know exactly where they should be removing tissue. The surgeon would like to share the data with particular colleagues. In fact, this particular surgeon has a colleague in Boston, and his real aim is that as he does the operation, some analyses should take place that should be made available to the colleague in Boston, who can then give him advice on his opinion on where the piece of tissue that should be removed is actually located. At the moment, he can't do that. At the moment, if he wants his colleague at Boston to have a look at the data, he writes it to a DVD and puts it in the post. And obviously, that's not helpful if you're trying to use the opinion of the doctor in Boston to govern where the surgery should take place. So in CARMEN, we're trying to tackle this to provide a way so the data and analysis codes can be shared irrespective of where the scientists are. And this is being done through a project called the CARMEN project, which is a EPSRC, so that's the UK Engineering and Physical Sciences Research Council. And it's quite a large project. I put $7 million. I've given this talk in the United States about 4 times in the last 6 months, and every time I give the talk I have to reduce that number because of the plummeting value of the pound. So it used to be much healthier when I first started to give these talks, but $7 million is still quite a lot. And we have a set of investigators around the UK. So the IT side of it, the computer science, is done by ourselves at Newcastle and Jim Austin's group at York, and I'll talk more about their work later. Then we have neuroscientists around the UK who are collecting information, collecting data, and trying to use the system to do their science. And we're grateful to some companies who are helping us out with this. So when you step back and think about what the requirements are for solving these sorts of problems, meeting the needs of these scientists, then I've characterized this under 4 headings. So first of all, we need to be able to store the data that's collected by experiments, and we estimate there'll be a few hundred terabytes of data by the end of the project. Then we have to have a way of analyzing the data, so we need a suite of neuroinformatics services that the scientists can use. Some are data intensive, so we need to have some processing power to back that up. One thing I'd stress about this, and this will come through in the rest of the talk, is that it's no good having a fixed set of services. Neuroscientists are clever people coming into work in the morning. They might have a bright idea for a new way to analyze their data. They want to code that up and apply that to their data. So we need a way so that we can not only share data to add new data into the system, but also to add new analysis codes into the system and allow those to be shared too. We want to automate the analysis where there's a standard way to do something that's been worked out. We want people to just be able to press a button when data comes in and get some results. And in other eScience projects, we've successfully used workflow, so we'd like to provide that. And we need to be able to, as I've stressed, sharing is something that's very difficult to do at the moment, and we want to be able to do that more easily, but it has to be under user control. So if you talk to users about making data available, if you say, well, we could create a public repository and you put your data and your services in there, then very few of the neuroscientists we work with would be interested in doing that. And the reason is that in their particular branch of science, they've got particular reward structures, there's a particular sociology of the way in which science is organized in neuroscience. It's not untypical, I think, across lots of sciences. And so what they want to do is they're very fearful of being scooped. So what they want to do is to typically go through a small number of stages. So they create some data in an experiment, they upload it into the system so that only they can see it. They do some sanity checks just to make sure it seems okay, and then they share it with a small group, perhaps their lab, the PhD students, the postdocs, and so on. And then once they're comfortable with that, they might extend it to other collaborators around the world. And then after that, once they've got the papers in Science or Nature, then they're keen to, they're often happy to make the data publicly available, but not before that point. So we need some sort of fine-grained sharing in the system. And Savas mentioned all the different sorts of projects we have. I tried to write some down the areas that have been working over the past few years. But this sort of these four different functions that we need do seem to be common to lots of the work that we've done over the years. So be able to store data, analyze it, automate the analysis, and to share it in a controlled way. And so as a result of this, if you ever saw one of my earlier slides on CARMEN, what we did was we lashed up the system using existing eScience tools to support what neuroscientists wanted to do. We've now stepped back and we've started to think about, well, what could we do to support a wider range of science so we could use this as a common framework across lots of different sciences in which we work. And so we came up with this idea of this integrated store, analyze, automate, and share platform, which could be generic across a set of sciences. So we're piloting it with neuroscience and also, as you'll see later, some chemical informatics. But the hope is that it's generic and we can use it more widely than that. We also started to do some work with these people, Newcastle Science City. So this is a big initiative in Newcastle to try and grow the science economy. And we started talking to people from there about what were the barriers to spinning off science companies from universities or encouraging science companies to locate into the area. And we started to look at the needs of those companies as well. And we started to work with some of those small companies in the Northeast to see if we can provide what they want too. And one of the key things about that was that they often are quite small and they don't have very good IT skills. And therefore, something which was simple to use was very important. So anything which required lots of deployments, lots of configuration, really ruled out a lot of these companies, and indeed a lot of the researchers with whom we work. So we wanted something simple. So we decided to try to go for this web-based approach. So basically, you can do almost everything by just using a web browser. So that was that was one of the driving goals that we had, and I'll talk a bit later about whether that's actually achievable or not. So to solve this, we came up with this architecture, which I now know to call a cloud. So again, in the early days when we first wrote the CARMEN proposal, which was 2005, the word cloud was never mentioned. It's just suddenly come up along the rails, and everybody's talking about it. And it seemed to us that actually when you read about what clouds were, and I'll talk more about that in the next slide, then that was basically what we were doing. So the idea is, as I say, people just use a web browser. They can upload their data. They can upload analysis routines. They can do their analysis out there somewhere over the internet, and they can share their results with others. When we were thinking about designing this cloud, this generic infrastructure to support these different range of scientists, then we had to decide, well, what actually was in the cloud? What was the basis that we provided for scientists to run codes and do analyses? And I thought it was useful to have a look at this taxonomy of clouds, which was produced by Robert Anderson from his blog. And he splits them into three parts. So at the top, he's got software as a service, which is this idea that rather than have desktop applications, you interact with applications through the web. And examples of that are things like Google Apps and also Salesforce.com, that's done very well by taking customer relationship management, which is typically something that was run through desktop and server applications, and moving that so it's just you can access it all through the web. And then at the bottom, if I can jump from the top to the bottom, you can see we've got the what he calls infrastructure as a service. This is what you get with Amazon, and also some of what you get with Microsoft Azure, as we heard in the tutorial yesterday. So this is the idea that you can just go out and grab, as you want, nodes, processing nodes, and also storage resources, and use them, and when you're finished, you can release them. And you only pay for them as you use them. So this is probably what most people think of as cloud computing at the moment, this infrastructure as a service. But there's also a lot of interest in this middle area starting to emerge, which is this idea of platforms as a service. This is where you think, well, if people have to write at this bottom level here, at this infrastructure level, there's quite a lot of a stack you have to write before you get up to the direct interaction with users. So is there some help we can give to users by thinking about the domain which we're trying to support in this cloud and providing some useful services for that particular domain? So an example of that would be some of the higher-level services that are in the Azure framework, things like data services, security services. It's also interesting that Salesforce.com, for example, started off as just a software-as-a-service cloud platform, and they've now moved down with their Force.com, and they've produced a cloud platform for people building business applications on their own infrastructure. So when we thought about this, we looked at that first option that I talked about just basically saying to people, there you go, here's a way to grab storage and processing nodes and get on and write your science applications to do your neuroinformatics. And we really felt that we could do better than that. If we could identify a set of services which we could run in the at that level there, at the science platform level, which would give help for people who are trying to write science applications. So based on our experience in lots of projects and what we'd seen around, we sat down and thought about what should be in this science platform in the middle here. And so we rejected that one. And so this is the idea that we provide this science platform. The scientists concentrate on writing their analysis routines, which sit at this high level up here on this platform we provide. And as far as users are concerned, this is just basically a software as a service offering. So they just bring up a web browser and interact with the system. And having thought about this, this is what we came up with as these set of services for our platform. So this is based on the previous projects we've had. So if I go around these reasonably quickly, you can, on the right-hand side, we've got all the different sorts of storage. So a lot of primary data from eScience comes in the form of files, so we need somewhere to store, to do file storage. And the people at York are very good at doing fast pattern searching in large data sets, so we've got some technology to do that close to the data. Then we've got a database for a lot of secondary data is structured, so we need a way to do structured data storage and retrieval. Metadata, I said earlier about the problems of trying to interpret the data that's out there, the problems of trying to search for data with particular characteristics, for example, captured in particular sorts of experiments. And so we've got a metadata store, a form of metadata for describing the neuroscience data we're dealing with has been designed. And so when people upload their primary data, they fill in a form and it gets stored in that metadata store ready for searching. And then I talked about the need for being able for people to upload services and to have those services run against the data. So we've actually got a service repository. So when you upload a service, it gets stored there and it gets deployed on processing resources as needed in order to process the requests from users. So this is what we have at the moment. When a user wants to do some analysis, they often want to use a workflow because that, as I said earlier, that automates the analysis. So we've got a workflow enactment engine in there as well. So users can create workflows, run them, and as they run them, services are called, and those services are taken from the repository and run on processing nodes. And just to give you an idea of, we've just moved to this new generic platform. So at an early stage, but we've got an Ajax workflow editor that works in the web. So you can grab some over here from a set of services. You can grab them and connect them up and then run your workflows. Once you've done that, you can look at workflow runs. And, of course, you can make those available to other people as well. So you can go and see what other people have been doing if you're allowed to do that. And you can see, as well as the result files, you can also see the workflow they use. And obviously, you can click through and look at the results if you want to. One thing we've been exploring is blogs. So we're influenced by other projects that are out there that are looking at this space. So projects like My Experiment, projects like Facebook in the commercial world, and SciSpace as well in this world. And so we're interested in the idea of blogs. And what we've been trying to do is to try and use blogs to see if we can link that to the data which is being used to do the analyses. So this blog here is from a guy called David Leahy, who's a chemist, and he's writing about some experiments that he did a couple of months ago. And these are the results of those experiments, also the primary data, the workflow that he used to analyze it. So somebody could, for those people who he makes the blog available to, they can go and not just read about what he did, but they go and look at the original raw data. They could then reanalyze it using his workflow, or they could use their own workflow, or they could try his workflow out on their own data. So it gives you this sort of, somebody called it a playground, this way in which you can play around with by looking at what other people have done and use that as a starting point for your own experiment. So this is what we did. I wanted to talk about clouds now, so I wanted to talk about our experiences. So actually what we did when we started, there wasn't, commercial clouds weren't available. So what we've got is our own clusters, which we use to run this software on. I'll talk a little later about moving to a commercial cloud environment. One of the things we discovered was that moving technologies into the cloud can be difficult. It's taken us much longer than we thought it would, particularly technologies which assume that you're running on a desktop and want to interact directly with a user. It can be very difficult to convince those to run in a server remotely, and trying to integrate those into the system took much longer than we expected. Another reason is because some applications just won't run there at all, however they're architected. So this is a very popular application in the project from York. So this is called Signal Data Explorer. And what this is a way of visualizing information. So this is information from a whole set of electrodes, which have been used to collect information from a slice of brain tissue. And it allows you to search for particular patterns, so you can identify a pattern, press search, and then you get all occurrences of patterns that are like that in your data sets. And the people at York had a look at trying to move that into a cloud, trying to give it a web interface, but really the level of interactivity of the data was just too high, and there was no way you could get a nice look and feel and user response for the sorts of things that users wanted to do. So this remains a desktop application. So I think that's one of the things that we've learned. Although we might have this goal of moving everything into the cloud and just having a software as a service web browser interface, not all applications are going to work well in that way. I think the second point I wanted to stress was about scalability. So a lot of the excitement about clouds is the fact that scalability, you just go and you grab however many nodes you want, and away you go, and you get your results back much faster. It accelerates the way in which you do science. I mean, a caveat is that if you look at structure as a service clouds, then what you find is actually that you don't automatically get scalability. So it doesn't magic away the problem of building scalable distributed systems. The old problems are still there. It's still up to developers to do that. So the potential's there for scalability, but your developers, your designers have to realize that. And I'm going to talk about very briefly how we did this in order to make a couple of points. So this is a system that we have called Dinosaur, which dynamically deploys web services as required to give scalability. So if you look at the left-hand side, you've got a client. It's going to send a SOAP message into the system. What the system does is to look to see where the processing resources are to run this. So it sends it to a cluster over here. And when it gets there, in fact, this is a request for a service S4, and S4 isn't deployed anywhere. So what it does is it sends a request to the service repository, gets a deployable version of the code, deploys it, passes the request, processes it, and then the result can come back. And the deployed service stays there waiting for other requests. And once you've got a service deployed, then you don't have to redeploy it every time. So this is a request for S2. And S2 is actually down there on that node, so no deployment needed, and the request comes back. So what you need in building these scalable clouds is a way to dynamically deploy services in order to meet user demand. And if you look at this graph here, this shows how you can add services to a set of nodes in order to achieve scalability. So this bottom graph here is the response time for a system in which requests are being injected at a particular arrival rate. It starts relatively slowly and gets up to a faster rate at the end here. And you can see that the response time here is relatively static. And the reason is because actually what's happening is the system, so Dinosaur in this case, is adding nodes. So it's dynamically deploying services on more and more nodes in order to maintain a reasonable response rate to users. And at this point here, the reason why the response time suddenly shoots up is because in our cluster we had 16 nodes, as you can see at the top, and once we've used them all, that's it. We can't throw any more at this particular service, and so the response time's bound to increase. So there's 2 points about this. So one thing that's important for clouds, particularly pay-as-you-go clouds, is that you don't just grab, say, 100 nodes and then use them as you wish, potentially with very low levels of utilization, because that'll be expensive. So what you need is somewhere to grab nodes as you need them in order to meet user requirements. And the corollary is you need a way to give back the nodes as soon as you don't need them, because you're going to still be paying for them if you keep them. And the second point is that, of course, one of the attractions of moving to commercial clouds is that it would avoid this limit here, because once we got up to 16 nodes here, we haven't got any more nodes in our cluster. I would have to put in a request for funding to expand our cluster. If I wanted to solve this problem, it's going to be a few months before we can do that, whereas on a commercial cloud, you could just go and grab more nodes if you're prepared to pay for them. So as I come to the end of the talk, I'm going to show you some examples which are hot off the press, in the sense that I was in Microsoft Reading on Friday near London, and they were just getting these experiments to work on the Microsoft Azure cloud. So this is a group of people who've been doing a proof of concept for the last 3 weeks down there. And they've been looking at two things. So one is using some Microsoft user interfaces on top of this type of application, and secondly, using the Microsoft cloud to speed up some of the things we've been trying to do. So here's I'll just show you a little bit about the application. So this is where you can select compounds. This one apparently is a joke among chemists about a Christmas compound. I don't know whether you can see that one. And then you've got this panel here, which allows you to decide what analysis you want to do, and you press a button. And when you press the button, an individual analysis can cause lots of different services to be called. And what happens is that if I move to this movie, let me see if we can see this. Okay. Just miraculously reappear. There we are. So on the left, these are the requests which have been sent to which have been queued up for the Azure cloud, which only has one processor allocated at the moment. And here's a response from one request, and then there's a response from the next request. So this is going to take a long time to get through all of those responses. So what happens now is, so this is done manually, but in a real system would be done automatically. We just grab another 9 nodes just like that by pressing a button on a box. And so now you'll see that now with 9 nodes running on this cloud, then we get one result quickly, and then in a little while we'll start to get lots of results coming back at the moment, and the queue requests will be cleared off quite quickly. There we go. So that shows the benefits of being able to just grab resources as you need them very quickly. And I wanted to end by just looking at, I'll go down here, why this is important. So one of the problems we have in research is that I always feel that the way that research happens is that you have a good idea and you write a grant proposal, which usually takes a few months. Then you wait about 6 months to get a response. And if successful, and in the UK, success rates are down to about 20% at the moment, so that's quite a big if, then you get the money that you need to buy the IT kit that you need to do the science, and then you wait another 3 months usually to start the project. By the time you've recruited somebody, you install the computers, and then you can start work. So you've got quite a gap between having the idea and doing the work. And cloud to become interesting to commercial companies, small commercial companies, for a similar reason, that at the moment, before clouds became available, you had this series of steps where you had the good idea, you had to write the business plan, try to get some VC to fund it. If you were lucky, eventually you got the money and you can install the computers and start work. And by using commercial clouds, the hope is that we now move to a model where you have a good idea and you just go and grab the nodes from a cloud provider, and then you start the work straight away. And you obviously have to pay, but you dramatically reduce the time it takes before you can do the work, and you pay for what you use. And of course, you get the advantage of scalability that I've talked about, cost and sustainability. You don't have to keep bringing in large amounts of capital to replace the kit that you have. So my hope is that commercial clouds could really change the way in which eScience operates by giving resources quickly as we need them to people who are trying to do data analysis. I think the problem at the moment is that a lot of the focus with using clouds in science is at this level here, this cloud infrastructure level, where commercial clouds are currently allowing you to grab processing resources and storage. But there's still this gap of a science platform, which means that at the moment, these science apps can't just survive up here, but you end up having to build them right down here, and you end up with a lot of software to build and support. And so that I think the challenge is how do we fill this gap here and allow scientists just to work at the level they're best at, which is up at the top here. So this is the idea of eScience Central, and because we're interested in not just pay-as-you-go infrastructure, but pay-as-you-go science clouds, we've also been exploring this through a company as well, looking at business models for this. Okay, so to summarize, one way to look at eScience Central and CARMEN is this combination of various technologies. So the software as a service, so you've got this web-based interface to do your work. You can do it from anywhere. Some social networking, which allows you to share and collaborate, create communities. And then cloud computing, so you can dynamically allocate resources. And when we move fully to commercial clouds, to do that on a pay-as-you-go basis. So that's really where I think we're trying to be, at the intersection of these technologies. And final summary would be that eScience Central, we're producing this generic infrastructure to do these four things: this store, analyze, automate, and share. And we're trying to do it across a range of sciences. We're piloting it at the moment for Neuroinformatics, which we see as being an exciting area of science in which eScience could really make a difference. And we're trying to use cloud computing, which we think could revolutionize eScience by reducing the time it takes from going from an idea through to the realization of that idea. Okay, thank you. I do.
At what level do you think actually introduction of standardization into the cloud platform, from the point of view of infrastructure as a service, platform, or software as a service, will it actually ensure that a thriving economy is built in this, rather than vendor lock-in and other things like that?
So I'm tempted to say I never want to get involved with standards ever again in my entire life after the great experience. But I guess it can be important. But I think the problem is that it's probably premature. I think that at the moment it would take the vendors to decide that it was a good idea to standardize, and I don't think that's going to happen at the moment. And in the middle area, that science platform area, I mean, I've suggested the sorts of services in there which I think are important. I think other people will suggest other services. For example, to some people, clouds are all about Hadoop, and so I'm sure that they would want other sorts of services in there. So I think there's probably a few years of trying to work out what really should be in that Science Cloud platform before we settle down and start to think about standardization.
And do you think universities, with your model about rapid provision of infrastructure, universities should actually, before this becomes prevalent, introduce some mechanism to actually oversee this? Because every researcher thinks he's got a good idea.
Well, in some ways, what this does is to democratize science, because any researcher who thinks they've got a good idea and they've got a little bit of money, and it can be a surprisingly small amount of money to run some reasonable experiments on these clouds, can go ahead and do it without having to go through the process of applying to use their university resources, or forming a team of people and applying for funding to get a cluster or a supercomputer into their university. So I quite like the way in which it frees people from having to go through bureaucracy before they can pursue the science that they think is important to them.
But it is still university money.
Well, I'm a little bit nervous about coming all this way just to talk to the neighbours. But very nice talk, Paul. What it occurred to me was, I think the challenge that we've all seen in almost all our applications, particularly in the data world, is the challenge of all sorts of legacy technologies and legacy work habits and legacy organizations. And yet your talk treats providing the platform as something of a greenfield site where you provide a science platform ab initio, so that nicely avoids all the problems of licenses and so on. How easy what sort of percentage of the things that the scientists will actually use in both data and code do you think you can migrate into this greenfield site, and to what extent does the rest have to be reached by external services?
Mm-hmm. So that's a good question. It's one that we struggled with in CARMEN, because if anybody had read the CARMEN proposal, it would not have mentioned one particular type of application environment which has been the bane of most of our lives for the last 2 years, which is MATLAB. And I've got nothing against MATLAB, but it turned out once we started there was quite a lot of neuroscientists in the project who relied on MATLAB, and trying to take MATLAB code and get it to play in this sort of space has been an awful lot of work, and we have made quite a lot of progress on it by compiling it and wrapping it as a service. But this is very true that there are lots of areas where people are using code which, because of licensing problems or just because it's legacy code, that you can't easily move into this sort of environment. And then you've only got two choices. You either have to try to use it externally, as you say, and call out, which we can do, so you call out to it as an external service, or you try to move the scientists to use something else, which there's a move among neuroscientists to use things like R, for example, rather than MATLAB. But one of the reasons why I'm hopeful that things might improve in this area is because of the commercial interest in clouds. So, for example, I don't know whether you saw a couple of weeks ago, but MATLAB released a white paper about how to run MATLAB on EC2, on Amazon EC2. Now, they would never have worried about running MATLAB on our CARMEN cloud, but because Amazon is such an important infrastructure now, lots of scientists want to use it, then there was a compelling commercial case for them to actually do the work to do it. So my hope is that with Amazon and Microsoft moving into this space, that some of those people providing scientific software for scientists, some of those companies may become much more interested in providing versions which work in this way.